Spielberg presents Back to the Future, a Robert Zemeckis film. Marty leads an ordinary life.
No McFly ever amounted to anything in the history of Hill Valley.
Well, history is going to change.
And 1985 is not his year. But Dr. Brown is about to change all that.
Are you telling me you built a time machine? What of a DeLorean?
He's sending Marty 30 years back in time.
It's a flying saucer from outer space!
Now, he's trapped in the past,
It's got to be a dream.
about to meet
Chocolate.
his future father.
He's a peeping Tom.
Wow!
And he's making an impression on his mother.
It's an absolute dream. And he can sleep in my room.
Anything you do could have serious repercussions on future events.
Now, he's got to make his mother and father fall in love.
For crying out loud, I haven't even been born yet.
And only Dr. Brown can help him get back to the future.
Are you telling me that this sucker is nuclear?
Precisely.
Michael J. Fox,
Whoa, this is heavy.
Christopher
All right, so this movie, we have this kid who is now in the past, and he meets his parents and trying to make them fall in love because his mom is in love with him, and that's awkward, weird. And so they go through this process of trying to get back to the future, to the present where they would be. And so in this movie, there is a car that they mention,
Year
and that
30.
car is called the DeLorean DMC-12. Probably one of the coolest cars out there. It is in a museum somewhere. And this DMC-12, this DeLorean car, is built to be able to sustain time travel. And so with this vehicle, they have to go a specific speed to be able to reach the time, to be able to time travel and travel through that. And so we're going to investigate the speeds of the DeLorean and how fast it needs to go to be able to reach the speed needed to be able to time travel. Okay, so the DeLorean. Doc, which is the older gentleman in the video, he kept a special notebook, and it recorded the speed of the DeLorean after 20 seconds. So it would accelerate for 20 seconds, and then it would take off. And it had a mean of 80 and a standard deviation of 7.7. So those are going to be two very important key concepts here. So I'm just going to go ahead and make note on my makeshift whiteboard over here. So we have a mean of 80. And so we can just say, not really sure if it's a population or sample. We're just going to call it a sample of 80. And he has a standard deviation of 7.7. And we're going to take these values and we're going to look at some practice runs and see at what rate is a DeLorean meeting specific speeds. And so we are on slide 5. So I'm just going to go ahead and make a note here. This is slide 5. It says, what percentage of the runs will give the DeLorean a speed between 64.6 and 87.7? Now, you'll see to the right of it, that is another way to say the exact same thing in mathematical notation. So notice how you have the X in between the 64.6 and the 87.7. And so if I want to know the percent, I am looking for the area between those two values. So since I have two values, I'm looking for the area, the percent. This is leading us to the bell curve. So we have our bell curve, and we know the value that goes in the center is the mean. In this case is 80. And we're trying to reach 84.6 and 87.7. And if I go up one time, I'm going to add my standard deviation, and that gets us to 87.7. So that's actually where we wanted to land at on the right side. And then I want to get to 64.6. So I'm going to have to jump backwards. And if I jump backwards, I'm going to take 80, and I got to subtract 7.7. And I land at 72.3. And I didn't quite get to the 64.6, so I'm going to have to jump one more time. And I'm going to take 72.3 and subtract the 7.7. And we get the 64.6. And notice we can section this off. So this was actually from the last unit that we did in Unit 2. The empirical rule is what we're going to use to figure out the percent of each of those parts of the picture. So we know in the center we have 34%, 34%, and then the left side of the 34% is 13.5%. So the probability that our speed is between 64.6 and 87.7 miles per hour is equal to, so we're going to take all of those values, 34, 34, plus 13.5. So we got 81.5%. That didn't work out in my favor. All right, so we get 81.5% of the runs will be between 64.6 and 87.7. All right, number 2 says what percent of the runs will give the DeLorean a speed less than 85? All right, so if you look at the picture that we just previously did, you'll notice that 85, we go from 80 to 87.7. So that means 85 is somewhere between the 80 and the 87.7. So when we look at example number 2, we have to ask ourselves, is the empirical rule a way we can get the percentages here? And in this case, since the 85 does not live exactly on a standard deviation jump, we can no longer use the empirical rule. And remember, the empirical rule was just to estimate what should happen. So for problem number 2, before we actually do the problem, I want us to go ahead and practice writing out what this would look like in mathematical notation. So the percentage, aka the probability that the speed is less than 85. So the way that would look like is the probability that the speed is less than 85. And so in our picture, this is gonna be the new part because we actually don't know how to figure out the percent when 85 is somewhere right here. Let me use a different color. When 85 is somewhere right here, that doesn't really tell us what percent we would get included because the 34, it's not symmetric. So this side of the 34 is a little bit taller than this side of the 34. So it's not symmetric, so we can't use this idea of cutting it and dividing it into equal parts. So instead, we're going to have to use something new. But let's go ahead and just draw a picture. Let's draw a fresh picture. So when you see a picture like this, the only thing that you really need in your picture is the mean. So the mean in this case was 80. So I'm going to plot 80. We know the mean is in the center. And then 85 is going to be to the right of the mean. So we're just going to plot, and it doesn't have to be perfect. We're just going to plot 85 and draw our anchor all the way up. And then we have to ask ourselves, okay, am I going above 85 or under 85? And because it says the word less than, and it's pointing to the left, we're going to shade everything underneath the 85. For instance, this one, we would have shaded everything between the 87 and the 64.6. So then now our goal is to figure out, well, how much did we just shade in that area? So how much is that piece right there? Okay, and so there we go. Probably that X is less than 85. And then here's our picture. Now, you really don't need anything else on this picture. You don't need the jumps with the empirical rule because we no longer can use the empirical rule. So we have to come up with another way. And in stats, our calculator will actually do this for us. But before we do that, we have to know the layout that we're going to have to write this in. So whenever you're looking for the area, so in this case, you're looking for the area. Or you could also look for the probability or percent. or proportion. All of these words are interchangeable. It's just the only one that's really different is this percent. That means you write your answer as a percent. The others, you're going to write your answer as a decimal. So when you're looking for the area, probability, percent, or proportion underneath a curve, we're going to use a calculator called Normal CDF. Normal CDF. And so you're typically going to always write a picture, the calculator command. So in this case, we're dealing with Normal CDF. And then the first number that goes in your parentheses is the lower bound. Now the lower bound, you get that from reading your graph left to right. So if we look at our graph, we're gonna start on the left side. So here's the left side. We ask ourselves, where is this going? What value do you think that is headed towards? And in this case, it is going to the left. So it's going to the negative side. It's going all the way to the left, and it's not stopping. It keeps going forever and ever and ever. So this is going to negative infinity. Now, your calculator, if you take a look at your calculator, I want you to see if you can find the infinity button on your calculator. Let's see. Infinity button. You may notice that there is no infinity button. Now, because there is not an infinity button, we have to tell it mathematically just a really, really, really large number. And to do that, we can use scientific notation. So remember, sometimes y'all got the E thing in your calculator at the very end. We can do that here, and we can say negative E99. That is another way to write negative infinity. It's basically a number with 99 zeros, and a very, very, very large number. And then we have our upper bound. Our upper bound is where it stops. So we go to the right, and we hit a wall, and the number we hit a wall at is 85. And then we have our mean. Our mean in this case was 80. And then our standard deviation was 7.7. And so this is the format of your answer, part of your answer. This is your work. You're showing that you found your lower, upper, your mean and standard deviation. And then from here, we just need to type it into our calculator. So in your calculator, what we need to do is we need to go to Normal CDF. Now to find that, we have to go to distribution. So distribution, you'll see it is a blue, it is on this row right here, and it's blue above the var. So you're gonna hit the blue button, distribution, and then we want Normal CDF. In this case, it's option 2. Now, depending on your calculator, you may see what it looks like in the picture on the slideshow where it says lower. It's asking you for your lower, upper, mean, and standard deviation. If you have an older calculator, it won't even tell you anything. It just puts some parentheses there. So we're going to need to know what goes first. So we have this negative E99. So we have a negative. The E is not the letter E. This E stands for a math symbol, not a letter E. And if you look, it is a blue button, and it's where the comma is, or above the 7. So you're going to hit second, and then the comma button, and then 99. And then we have comma 85, comma 80, comma 7. Now, if you have the newer calculator, you'll just hit enter, and you'll type in each of those pieces there. And then we'll hit enter. Oh, I hit enter twice. And then we can see our answer is 76. 2, 4, we'll do a 7 there, okay? Now, the question did specifically said what percentage, so we're going to take this value and we're going to write it as a percent, so that's going to be 76.247%. And if we look at our picture, if we have an answer of 76.247%, if you look at your picture, you clearly shaded more than 50%. It was definitely more than 50, so your answer should be more than 50%. So you can always gauge it that way. We can also always guess what we think our answer should be before working these out and make an estimate and using that ish number idea. Okay, let's try another. And we did not round to 3, but that's okay. All right, so now we're on to slide 6, and we are going to, I want you to practice. On number 3, I want you to see if you can, 1, draw your picture and label it, write your calculator command, and then round your final answer to 3 decimal places. All right, so hopefully when you're drawing your picture, usually I like to start with the picture, but for this problem to start with, actually, if you haven't done so already, let's go ahead and write it as an inequality with the mathematical notation. So we have the probability that x, and because it says more than, we're gonna use a greater than 68.45. And also, you will never have to use the empirical rule again. Okay, the empirical rule is just a way to estimate. With normal CDF, it'll actually tell you the answer without the empirical rule every time. It's the exact answer. It's not an approximation. All right, so in your picture, we have our bell curve. And we know 80 is in the center. So the 68 number should be over here. We're going to anchor it down. And then we got to decide which way to shade. Now, because it says greater than and it's pointing to the right, we should be shading to the right. I want you to come up with a ish number. Let's see. I want you to think, what do you think it should be? We're just going to guess. Doesn't have to be right. Just guess. What do you think your area, your percent, should be about? I'm going to guess about 80. I'm just going to say, I'm going to do 85%-ish. So that's my guess. Let's see how close we get. Maybe yours is different, and that's cool. We're just going to see how close we can get. Okay, so we need our normal CDF. Normal CDF. And then we need to put what's going in the parentheses. So remember, we go, if we looked at the previous, the lower bound to upper bound. So the lower bound is where you read it left to right. So you're going to start on the left side. So if we look at the left, so we're reading it left, and here is where it starts. It starts at 68.45. So that is our lower bound. And then we keep going to the right, and I never hit anything. It just keeps going forever and ever and ever. So that's telling us we are headed to infinity. So just like the previous problem where we went to negative E99 because we went to the left, to the negative side, how do you think we're going to write this one in terms of infinity? Okay, so we get E99, and then we have our mean, and we have our standard deviation. And then from there, it's just some calculator work. So we're going to go second VARS, normal CDF. Our lower number was 68.45. E99, 80, 7.7. And we get 93.93319. If we write this as a percent, we get 93.319%. And that would be this area right here. That's where we did not know. I was kind of off, not entirely close to the 85, a whole nother category over, but 93.319% we get in our area. All right, so now that we've seen 3 different examples here, I would like you to do the next one on your own. So I want you to write what is the symbol notation we can use for that. the picture with the labels, the calculator command, and then round your final answer to 3 decimals. We'll just keep it to, 3 decimal places, so 3 numbers behind the percent. All right, so now that if you've done that, hopefully you have, and you answered the question, let's double check. So what you should have gotten, we have 83, E99, and then our mean 80, and then 7.7. So you should have gotten 34.8412% on this question number 4. And that tells us about 35% of the runs were more than 83 miles per hour. So not very many were that high, but about 34%. All right, so that concludes slide 6. So let's see. These were figuring out what percent that would fit that criteria of that speed. Now we're going to go the other direction. How fast does he need to go? Okay, so now we're on slide 7. How fast does he need to go? So what speed does a DeLorean need to hit to be in the top 16%? So if we think about our empirical rule, we know our empirical rule. We have some famous percentages, and 16% is a famous one. This is question A. If I use the empirical rule, because we haven't learned otherwise for this type of question, we know the mean is here, and we cut it 3 times. We have this guy right here is 0.15%, and this one is 2.15%. So that's 2.35. My bad. So that's 2.5%. I need 16. So if I go to this one's 13.5%, and that gives me the 16%. So that means I have all of this shaded, and we're trying to figure out what value creates that boundary. And the way the notation looks like, you have the probability that x is greater than x naught equals 0.16. So that 0.16 is how much you shade. Okay, so that is how much you're shading here, the 16%. This, the x naught, that's kind of new. So that x naught is saying, hey, what's that number there? Okay, that's connected. And then notice the direction we shaded. We shaded to the top, which is greater than. And if you look at the symbol, let's do blue. If you look at the symbol here, that tells you to go to the right. So we shaded to the right 16%. And to figure out that value, we actually kind of already know this because of the previous problem. We had 80 and then 87.5. So we knew this was 80 and this was 87.5 just from the 87.7. 87.7. Just from the empirical rule that we used, and we jumped and we landed there at 87.7. So to be in the top 16%, he has to go 87.7 miles per hour. That's how fast the car needs to go. If we look at B, first thing I would like you to do is read B and then see if you can write it with notation like A was presented to you with the X naught. So go ahead and try to write that out for B. Okay, so hopefully you got this. The probability that X is greater than X naught equals 0.15. So now you may be looking at the previous problem. We had 16%. Well, there is no way for you to get 15%. If you take away any of these numbers, you will never get to 15%. So this is where our calculator is actually going to be very helpful. So we're going to go ahead and draw our picture, but we're stepping away from the empirical rule. So here's our picture, and we know we shade 15%, and the direction we're shading to the right. So let me highlight here. So we're shading 15%. to the right. So when you're putting your line down, you don't want to put your line here and then shade to the right, because that's way more than 15%. You have to be strategic where you're going to place it. So 15%, if I were to place my line, I know it's less than 16. So I'm just gonna place it maybe like right here. And so we know our answer, if the mean is 80, we know our answer should be more than 80. And this area that I'm shading here is 0.15. 15%. So to figure out what value that is, if I were to guess, if I had an ish number, I would guess 90 miles per hour ish. Okay, that's my guess, just because the previous problem was 87.7, so it's a little bit more than that because it's 15%, not 16%. And so I'm guessing 90. So to figure out the actual value of this, we have our picture, the 0.15. We're looking for the x value, the speed that is associated with it. And so with our picture, we are going to have to fill in, and this is going to shift us to inverse norm because you know the area. This one, you are looking for the area. You are looking for the area. Here, you are looking for the x value. You are given the area. Therefore, we have to use inverse norm. We're doing the inverse of normal CDF. So if I take the inverse, to do that, inverse norm, first we need the area to the left. This is super, super important. You have to have the area to the left. Right now I have the area to the right. So what would the area to the left be? Okay, so we're gonna go ahead and label that. So that's gonna be 0.85 because we know the areas have to add up to 1. So we have area to the left, 0.85. Our mean is still the same, 80. And our standard deviation, 7.7. So this one only has 3 numbers, where the other one had 4 different numbers. So now in our calculator, exactly where you found normal CDF, so under second vars, where we had inverse normal CDF option 2, we're going to go 1 underneath it. So that's the one we were using, number 2. Inverse norm will allow us to undo it, and it's going to ask for the area. Now, it's not going to tell you area to the left. It's just going to say area. You have to know it's going to be just the area. And so our area is 0.85. And then we have 80. And we have 7.7. If you have a newer calculator and it has the options left, right, center, I highly encourage you not to touch those because it may get confusing when we do other things where that's not an option. You have to know how to find the area to the left. And so if you get too comfortable with it, it may hinder you later on. If you want to try things and hit some buttons, that is fine, but there is going to be an extra step that you have to write, and I'll show you that in just a second. So we get 87.981. And that's going to be our miles per hour. That's how fast he needs to go to be in the top 15% of the speed. 87.98. Which I was not too far off. I had 90 was my guess. So 87.981. Let me go ahead and box in. Oh, I circled it up there. That was the answer up here. Okay, so if your calculator has the left, right, center stuff, what you would need to do is in your calculator command, so if you have a newer calculator, I don't suggest this, but if you just want to do it this way, I'm not going to force you one way or the other. In the inverse norm, if you put 0.15, 80, and 7.7, and you change it from left to something else, you have to write it out. Okay, that is telling me that you know this is the area to the right, or to the left, or in the center. You have to say that. Otherwise, if you don't, I assume this is the left area, the area to the left. And if you don't write right, it's now wrong. Okay, so you have to make sure you include that. Otherwise, I'm not sure what you're putting into the parentheses. Okay, so to be in the top 15%, he has to go 87.98 miles per hour. And we know he has to hit the top 15% to be able to travel back in time. Otherwise, he's not going to make it, and he's going to crash into the building in front of him. Okay, so he has to hit 87.98 miles per hour or higher to be able to time travel. Let's see if he hits that speed.
Calculations are correct. When this baby hits 88 miles per hour, you're going to see some serious shit.
Jesus Christ, Doc, you disintegrated Einstein.
So Einstein's the dog that was in the car that now has time traveled on his own. And so we can see that they did end up reaching the 88 miles per hour, and the vehicle ended up time traveling. And so this was the part of the movie where they have figured out how now to travel through time and get back to the future. Hint the name, Back to the Future. So I thought that would be a fun little tie-in, kind of funny. If you ever feel like you need to watch the movie, it's kind of cringy, but it's kind of good.
Calculations are
correct. All right. So let's move on to a new context, new problem. We talked about Back to the Future. Now let's apply it to some sports. And I really love this problem. So we have this thing that's happened in baseball called the Maryland's Miracle. And so with the Maryland's Miracle, the Miami Marlins star pitcher Jose Fernandez was killed in a tragic accident, in a boating accident that kind of flew up on the shore. And he grew up in Cuba and traveled to the U.S., where he made his success as a local hero in Miami on the Marlins team. And so he was a very, very important player to this team. And so this was the game right after he passed away. The next day, they still had a baseball game they had to play. And so you can see 16 is on the field at the pitcher's mound. That was his number that he had. And so this was the important scene that came from that accident in the game.
Gordon has started to look like the D. Gordon of last year. Going to right. It's deep. And it's gone! D. Gordon has hit it out, and the Marlins have a 1-0 lead.
I don't know if y'all noticed either that they all of their jerseys say Fernandez, which is very powerful, and just to show the impact that this person had on them as a team. And so we have Gordon, who was able to hit first pitch off and get a home run from that
Gordon
first
has
pitch.
started to look like
So
the D. Gordon.
let's investigate this a little bit. So Bartolo was the pitcher in this game. His nickname, I thought it was funny, Big Sexy. He is like a bigger guy, and he's 46 years old, which is like, he's fairly old to be in the league. This was in 2016. And he had a speed, his mean speed of his pitches was 89.4 miles per hour. And his speed had a standard deviation. It varied by 1.7 miles per hour. And so we're going to kind of investigate some scenarios with his pitching average and kind of play around with those numbers and then see what happened with this pitch, because there's something happened with this pitch that we need to investigate. So let's look at A. Almost all of his pitches were between what two speeds? So when we think of like almost all of his pitches, we're on slide 11 here. Slide 11 on A. When we look at his pitches and we think about the bell curve, all pitches typically are between 3 standard deviations. So you have your mean, and we typically go out 3 times, and we're able to catch pretty much all of the data. In this case, it would be 99.7% of the data. Almost everything will be between these two values in a normal distribution. And so we need to figure out what are those two speeds. We know his his mean is 89.4. So what I would like you to do is to figure out what are the two speeds, the upper speed and the lower speed, that would capture almost all of his pitches. Okay, so hopefully you figured that out. We're going to do 89.4, and instead of adding it 3 times, I'm going to use repeated addition as multiplication here, just for time's sake, and we land at 94.5. And then I'm going to do the same thing, but instead of adding, we're going to subtract 84.3. So almost all of his speeds are between 84.3 and 94.5. Okay, so very rarely is it higher than 94.5 and lower, like very, very rare. Everything will be between these two values. What percent of his pitches were at least 86? Okay, so at least 86. So B, if I were to write that with my notation, I'm going to give you some time to see if you can write that. Okay, so the probability that X at least means more than or equal to, greater than or equal to 86. Now remember, we do not have to use the empirical rule on these types of questions anymore. We don't have to know each individual percent. What we can do is draw a picture. So in our picture, we want at least 86. We know 89 is here, 89.4. So 86 is somewhere over here, 86. And then we have to ask ourselves, which direction am I going to shade? In this case, it's pointing to the right, so we're going to shade to the right. Now, you may be noticing that this has an equal sign because it did say at least. It doesn't matter if it's equal to or not equal to, you're still putting your boundary on that value, and it's not going to go past that number. So with probability, it actually does not matter if it's going to be equal to or not, because the probability that's on exactly 86 is not even existent. So we don't have to worry about the symbols with the line, the equal to or not. Okay, then so from here, because we know we need the area, we need to think back to, okay, what calculator do I use, inverse norm or do I use normal CDF? So normal CDF, let's recall, is when we're looking for the area. Inverse norm is when we're given the area. In this case, I need the area, so we are going to use normal CDF. We have our lower boundary. It goes all the way to E99 infinity. Our mean, 89.4. Oops. And our standard deviation, 1.7. And then from here, we go into our calculator. Second vars, normal CDF, 86, E99, 89.4, and 1.7. And we get 0.97725. We want 3 decimal places for our percent, so we get 97.725%, and we have those 3 decimals right there. So we have about 97% of all his pitches. Almost every pitch he throws is above 86 miles per hour.